We're starting Module B, which is intersection control and actuation. Like all good stories, they often begin with a phrase that says, "Once upon a time." And I want to be right in there with all good stories, so I'm going to start in the same way. Once upon a time, the streets were narrow, cars were loud, there was no right turn on red. Whenever cars started, we knew that the traffic signal had changed. Corners were rounded, all pretty much the same. Curbs were curbs. They were high enough so we could detect them. That was once upon a time. And it looked something like this. In the olden days, the intersection controllers all worked on a fixed timed or pre-timed basis. So we knew exactly how long it would take for the light to change. They were predictable, and the lights would rotate through a defined cycle in a constant fashion, so we knew what to expect. Those kinds of signals are still sometimes found in downtown areas where there's a lot of regular traffic, not a lot of change. So there's a change every 30 seconds or so, regardless of what the traffic flow is like. And so in those kinds of situations, it was easily identified. There was an easily identified surge of traffic as the traffic started to move. A blind person could listen through a couple of light cycles and figure out the sequence and know exactly when to make the crossing. And there was usually a good amount of traffic that was moving parallel to the path of the traveler, which could be used for good alignment purposes. That was once upon a time. Now the times have changed. Signal timing is much more complex. The streets are wider. Right turn on red is everywhere. It's the law. Intersection designs have been changed to accommodate larger volumes of traffic, and it's confusing. Curb ramps are common, and the designs vary quite a bit, and where they're placed varies quite a bit. Even the cars have changed. We have hybrid cars. We have electric cars. Sometimes they're silent, and especially when they come to a stop at an intersection, they may shut off and be completely silent. There was a need for greater efficiency, and that's what changed so much of this. More traffic meant busier streets, wide radius corners, and channelization, special channels that would allow cars to make right turns, keep them away from the major flow of traffic. There were islands that were inserted, and crosswalks are no longer always straight. They sometimes have bends, and we even have roundabouts. We'll be talking about all of these things. So there have been great changes in intersection control of the signals. There are multi-phase controls. We have a lot of use of actuation. We have cycles that are not always the same. The lengths change. All of this controlled by these boxes at the corner that are very, very technological in nature, computer-driven, able to make variations depending upon the traffic. This is the kind of intersection we sometimes will see. We have multiple lanes. We have channelized intersections that move traffic away from the main flow. We have crosswalks that are not straight across. They bend. We have sometimes these little islands, medians, sometimes they're called pork chops. Wider streets, more traffic, difficult situations. Another example. The traveler walks, maybe he has to stop at this pork chop, so to speak. There may be another signal box to push. Maybe even having to change direction to make the crossing. Very complex. So we have new intersection controllers. There are semi-actuated controllers where the major street, which we call the arterial, rests in green unless there's a demand on the minor street, and the detectors are only on the minor street. Or we have fully actuated controllers where the detectors are on all lanes approaching an intersection. And when the traffic volumes vary widely over the course of a day, we see lots of changes occurring based upon those detectors. We even have actuated turn lanes where detectors are used to actuate the turn phases. Signal phasing is something that we need to really understand. Phasing plans can vary in their complexity. The modern controllers that I've shown you a picture of provide a tremendous amount of variation and flexibility. They can have protect movements. They really can do quite a bit to vary the design. The two-phase operation, which is the simplest, each street receives one phase in which all movements are made. So in phase 1, all the perpendicular traffic flows. In phase 2, all the parallel traffic flows. This is a schematic of what that might look like. Here's a three-phase operation. It adds a left turn phase, and that's most common. It's based on a left turn or a right turn. It may include a pedestrian phase, and the left turn design is critical. There's a period of time when only left turns are made, and that can be very confusing to the traveler, or right turns. An example of what that would look like in a schematic. Then we have split phasing, which provides separate green times or go times. One street may have concurrent movements, northbound and southbound. Another street may have one movement, westbound, including turning traffic, then a separate phase for the other movement, which is eastbound, including turning traffic. So they won't all go at the same time, even though they're on the same street. A schematic. We have left turn issues. Sometimes we have the cars that lead before the light changes. Sometimes it's after the light changes. Very complex. There can be a four-phase operation. Phase 1 turns, then the perpendicular traffic, then a different set of phase turns, and then the parallel traffic. So all of this needs to really be understood so that our travelers can remain safe. Here's an 8-phase operation on a very complex intersection. There are some intersections that are so complex that it may be necessary for the traveler to seek assistance in making the crossing or to avoid the crossing altogether. So how does vehicle detection work? There are what we call inductive loops that are buried in the ground. They're magnetic, they can be ultrasonic, they can be microwaved, even from a pole, infrared or video cameras that detect the approach of the vehicle. You can see in this picture that these are loops that are buried in the ground. Here's another example as the car comes up to the intersection. The weight of the car, not the weight, the mass of the car, the metal, is detected by those loops. So in a semi-actuated intersection, the major street is assigned the go, or the green, unless the pedestrian or a vehicle is detected on the minor street. So when the minor street gets the green or the go-ahead, the first vehicle is provided with a minimum green or a minimum go period, and then additional vehicles extend the time up to a maximum time. So if one car is leaving the area, the light will change typically for 5 to 7 seconds. Approximately 4 seconds for the light to change back to green for the arterial. So it's a total basically then of 9 to 11 seconds for somebody to make that crossing. We know that on smaller streets, 7 seconds will do it, but on a wide street, 7 seconds won't do it. So if there's more than one car, the first car typically gets about 5 seconds. Now, every other car will get an additional 2 more seconds as they roll over the detector. And maybe up to a maximum of 10 cars, so it is timed to some extent. Then there are a few 4 seconds for the light to change back to green for the arterial. So that tells you how much time we would have, including that changing back. So when we talk about vehicular timing at an actuated intersection, the length of the signals will vary upon the traffic demand, and each leg may have different phasing and different timing. So where does this put pedestrians? Well, first of all, we have something called the pad head, and that's the visual walk, don't walk signal. We also have at the corner a pedestrian detector or push button that the pedestrian has to push. And that's called a ped call, which lets the traffic controller know that the pedestrian is there, so that the pedestrian gets a pedestrian phase, which is a calculated time for the pedestrian to cross the street, based upon the average time for someone to make that crossing. But it requires that the individual push that call, push that button. The pedestrian signal indications. The walk interval, there's a sign that goes on, it's a walking person. There's a pedestrian change interval, a flashing don't walk, or sometimes it's a flashing hand. And then there's a don't walk interval, period, which is a solid or a steady hand. And we can see that as sighted people. As we cross the street, we can look and see those indications. So the typical timing for these signals, the walk interval, 4 to 7 seconds on a car. The change interval depends on the width of the street, but it's based on a calculated walking speed of 4 feet per second. And so we have pedestrian phase actuation where the pedestrian can affect the timing. If they push or activate the push button. If it isn't pushed, the pedestrian will not get the pedestrian timing. But if it is pushed, the cycle oftentimes starts during the following cycle. So it doesn't start immediately. So, if pedestrians try to cross an arterial without pushing the button, they won't get the pedestrian timing. They'll have the car timing. They may only get 11 seconds to cross with a single car, when if they had pushed the button, they might get 30 seconds or so. Now, what happens if there are no cars there as a queue? And that could be common throughout the day on some of the minor roads that are crossing major roads. It's often common where there's intermittent traffic. And of course, sighted pedestrians can see the pedestrian signals, which is the time the traffic engineer calculated as the best time for pedestrians to cross. But pedestrians who are blind or who have low vision usually don't have access to that same signal information. Now, there's something else that we have to consider, and that's called exclusive pedestrian phase. I call it in the manual scatter lights. That's when everybody can cross at the same time. Sometimes it's installed for pedestrian safety. All vehicles have a red signal. All the crosswalks have the walk signal at the same time. Crossings can be made diagonally, but right turn on red can still be permitted. This could be beneficial for pedestrians that have mobility impairments, but the fact that there aren't cars around, it's a real disadvantage for travelers who have visual impairment. And there will be crossings like that our students, our visually impaired students, will encounter. There are also leading pedestrian intervals. The walk interval begins before the vehicular green. which is intended to give the pedestrian a head start. However, this is kind of a problem for a visually impaired person. It's great for somebody who can see the signal, but not for somebody who can't. So pedestrians who are blind aren't aware of the leading interval unless there is an accessible pedestrian signal which is installed.
Sorry, I'm not able to search for that.
Thank you, Alexa. Analyzing traffic signal intersections. It's very important that all of our students be able to do this, and we have to give them practice in doing this. These are the steps that we would go through. First of all, determine the geometric configuration. Is it a plus-shaped intersection? Is it a T-shaped configuration? Are the streets offset? We determine this by listening. Then we have to have them examine the traffic flow. What are the directions of the traffic? Based upon the sounds of the cars, how many lanes of traffic? How intense is the traffic? And much more difficult to determine is the consistency. Does it change throughout the day? Maybe very little at one time during the day, but very intensive at another time during the day. Step number 3, determine the physical characteristics. What is the street width? The slope of the ramp towards the corner. How steep is it? Where is the ramp placed? Are there channels or median strips that we have to deal with? What's the type of curb? Are there truncated dome tiles at these corners? Can they see the crosswalk lines if they have low vision? And if there is APS, accessible pedestrian signals, are there locator tones? Can they be easily heard? And then really figuring out the type of traffic control. Is it stop sign, stop light? Is there no control? Is it a one-way stop, a two-way stop? Is it timed, or is it fully actuated or semi-actuated? Is there a turning phase? And what other timing issues might there be? All of these things really have to be analyzed before somebody makes a crossing, especially when somebody is making a crossing for the first time and they've never been to that corner before. Number 5, we have to think about the procedures to be used. We know there are different procedures when it's completely quiet, when there's intermittent traffic, when there's continuous traffic. We know that there are times when we have to use the timing method because we have periods that are of uncertainty, especially with uncontrolled traffic. We want to know, can we determine there's a surge through the light? Through the light with the traffic. We have to determine, is there an APS signal there? Is it best for us to cross clockwise or counterclockwise? Should we think about asking for assistance rather than even attempting that particular crossing? Is it possible to seek an alternative route? I have even come into situations where I have seen an intersection so complex and a person not able to deal with it, and the person has taken a bus prior to the intersection, had the bus travel through the intersection, and then gotten off the bus at another corner. So there are all kinds of interesting ways of dealing with these issues. The MUTCD warrants signalization. What is a warrant? They look to determine whether an APS is warranted. And certain conditions have to be met before they'll put in an installation. There's a process to determine if the signal APS is warranted. And they will have a transportation professional do an analysis of the intersection. I'm mentioning this because you will want to get in touch with the city and with traffic engineers, because there will be times when you will ask for an APS to be put in because the intersection that your student will be crossing on a regular basis is too dangerous without them. So you have to understand the municipality structure. Intersection signals could be controlled by the state or the county. New construction sometimes is contracted out. Signals may be maintained by different departments. There may be a local jurisdiction ADA coordinator that you'll need to know. So you're going to have to check the city website or phone directory to find out the office and the structure, because you're going to be dealing with these signals and trying to have them put into place from time to time. So how to contact the transportation professional. Call the department managing traffic signal, the department that manages traffic signals. Explain your professional responsibilities as an O&M specialist and why you want the intersection information available. Ask for more information regarding their responsibilities and find out the procedure for getting modifications to be put into place. It's helpful beforehand if you get to know these individuals and you show your interest to the public. There are engineering meetings, there are local disability advisory committee meetings, there are transportation improvement plan hearings. The more you become involved in these kinds of activities, the easier it is for you to make changes in the future. Educate yourself. Keep informed of where those APS installations are. Learn about the language. Familiarize yourself with state regulations and practices. Learn what the community wants. Remain informed on the current APS systems that you have. Follow up on requests and learn where to report problems. That will really be helpful to your students in the future. Also, please educate your visually impaired students. Let them know about the changes in signalization and geometries. How important it is if there is a button that they must push it to get that pedestrian phase. Talk about timing plan variations. And also work with them on advocacy. They can request an APS, and that can be actually more effective than you requesting it on your own. So advocate for APS when? These are the times. When a person can't discern the walk interval, when the pedestrian push button calls the pedestrian phase, and signalization would include leading pedestrian intervals, exclusive pedestrian phasing, or where there are many electric or hybrid vehicles on the road. All of these things may require the use of an APS.